All right, in today's video, I'm going to talk about finding equations of motion. So, in past videos, I've talked about the kinematics equations. Um, when I say equations of motion, I'm talking about describing a particular object's movement. And uh, we're going to use three things: position, velocity, and acceleration. Okay. At this point, we know what position, what velocity, and what acceleration is. Um, the equations of motion for each one: position is going to be labeled x of t, velocity is going to be v of t, and acceleration will be a of t. And this is sort of the other thing to notice about these equations. When I say of t, right, this is kind of like saying f of x. Well, in fact, it's actually really the exact same thing. Where f, right, is your function and x is the variable that the function depends upon. In this case, our functions are position, velocity, acceleration, and they all depend on t time. Okay, so in this way, we are actually depending on time as well as depending on, so we're actually looking at time as well, in case you were kind of wondering, where did time go? And so once we get each of these functions, what they'll tell us is for any given time, what the object's position is, what the object's velocity is, what the object's acceleration is. I should note, I'm using the word position here, but oops, I got the eraser up. But you'll notice that, when I give the equation, this will really look like displacement. Okay. All right. So the equation, well, we're going to start with acceleration actually, because acceleration's the easiest one. So it's a of t equals a constant number. Okay, so we'll just say constant, meaning an example here, I'll write examples in yellow, is a of t could equal 9.8. All right. So that's a constant number. It could be any number there. It could be a negative number. It could be a positive number. Doesn't matter as long as that number is unchanging. In fact, we should notice here there's no t dependency, right? Which is why if you've watched my motion graphs video, the acceleration is always a constant straight line, flat line. Okay, velocity. The equation for velocity looks like your initial v naught, or your initial velocity, plus at. Okay. We should notice that this looks pretty similar to, let me write down here, y equals mx plus b. All right, if we had learned that equation as y is equal to b plus mx, which is the same thing, notice, look how similar that looks. Okay, and even better if I write f of x equals b plus mx, right? We know that these three are the same thing, okay? And we all know that they make a line. Okay? So in this case, our velocity, an example will be something that is a line. So v of t equals, let's say, 2 plus 9.8t, okay, which is telling me my acceleration is 9.8, my initial velocity is 2, and my velocity changes in time as a line. Okay, and the final equation we're going to go over, position. Position equals x naught, in other words, initial position, plus v naught t plus 1/2 a t squared. Okay. Another type of equation we should recognize, right? If I had written f of x equals c plus bx plus ax squared, right? In other words, f of x, if we're just rearranging the terms, which we can do because addition is commutative, okay? These two equations are the same thing. We'll recognize this as, or both of these equations as, quadratic, okay? Which means our position is going to be a quadratic curve, okay? Or a portion of a quadratic curve, right? Because for us, time should never be negative, right? So if we have a parabola, it's a very messy parabola, our parabola, we don't care about what happens on this side of the axis, right? If time is on the x-axis here and position is on the y-axis, right? It doesn't matter what happens because we know time can't go below 0. Let me erase that just to kind of clear it up here. And then I'm going to show you an example of what a position equation of motion can look like. Okay. So kind of continuing our example from acceleration and velocity into position as a function of time. Let's say, it started at 0, right? Because 0 is valid. 2t plus 1/2 9.8 t squared. Okay. And you would multiply the 1/2 times the 9.8. You can simplify that to 4.9. But these three, right, equations of motion could describe a single object as it moves over time. Okay. So in this particular object, if for some reason, well, let's do this. Let's make it negative here, and you'll see why in a second. So I made those 9.8s negative, which should just have the effect of flipping the acceleration. And in this case, this would be an object that you threw downwards, right? So let's say you were standing and you called the height that you were standing, your shoulder height as 0, right? Because you can define anything as 0. And you were standing on this cliff and you threw a ball down. You gave it an initial velocity of 2 meters per second. And gravity has a value of negative 9.8 meters per second squared. And actually, I realized I've made a mistake. And this is why having those sign conventions is so nice. Because if you threw it with a velocity of 2 meters per second, you actually threw it straight up. So let me correct that. You give it a velocity of 2 meters per second straight up. It's got an acceleration of negative 9.8 meters per second squared. So what's going to happen? Right, eventually it will start falling down. Okay. So final thing to say about this is, how do we actually go about creating these equations of motion? Well, uh, you know, the things you're going to need to fill in if you're trying to get position as a function of time, you need to get x naught, v naught, and a. Okay. Once you have your x naught, your v naught, and your a, you just put them in. Okay, right? You just fill them in. For velocity, you need v naught and you need a, right, to get v of t. And to get acceleration, well, you need that constant. You need acceleration, right? In other words, a. Okay. So for all of the equations of motion, acceleration is a good place to start, right? And then go to velocity and then go to position. Okay. How do you get x naught, v naught, and a? Those are usually given in the problem, or if in the case of an experiment, that would be from your data, right? X naught being your initial position, v naught being your initial velocity, right? So for this person who was throwing the ball, if they were trying to create a equations of motion as a function of time, they wanted their x of t, their v of t, and their a of t. They would know, because they're on Earth, that acceleration is always negative 9.8 meters per second squared, right? They would have had to tell us the initial position, and in this case, they defined, right, which is okay to do. They defined the initial position, right, their shoulder height as 0, and they measured how fast they threw the ball. They threw it 2 meters per second upwards. Okay? And just knowing these three things, they can now determine where the ball is at any given time ever. So this is pretty cool. And this is why we care about equations of motion. Okay? In the case of our rocket ships, right? If we have these, we can know exactly where they'll be at any one moment. And our rocket ships aren't going to hit this ball. You might be thinking, okay, well, these equations will only make sense until it hits the ground, right? Right, and once it hits the ground, it might bounce a couple times, but it'll stop eventually. Well, rocket in space, right? Uh, might have a uh, real long time before it actually hits anything, right? You know, the nearest planet being quite far away. So, okay, I'm gonna wrap this video up.